So with that, we welcome Michael, and please take it away.
All right, thank you, Chris, for the very kind introduction, and thank you all for inviting me here. So before I begin, I want to take some time to acknowledge my advisors, Sergey Levin and Tom Griffiths, as well as all my collaborators here who have contributed to the research that you're going to see today. So I'll start by reflecting on the similarities between where we are today with deep learning and where we were with computing 100 years ago. So back then, we designed specialized electronic circuits for each different task. And in the past decade, we've been training specialized neural networks for each different task. Back then, we had feed-forward control circuits. Now we have feed-forward neural networks. Back then, we had feedback control circuits. Now we have recurrent neural networks. And even the ways that we describe neural networks are borrowed from how we describe electronic circuits. So terminology like gating. And for those of you who are around during Torch 7, the Lua Torch 7 days, we also had nn.parallel and nn.sequential. Like terminology like this has, terminology like these all have direct analogs with electronic circuits. And how we draw neural network diagrams look essentially the same as how we draw electronic circuit diagrams. And one of the breakthroughs of the 1940s was the von Neumann architecture that used a processor and a memory to implement a general purpose circuit, electronic circuit for solving many different tasks. We are now witnessing the integration of large language models and search, such as in Bing, Google, U.com, and Perplexity AI, all of which also use a processor, which is the large language model, and a memory, which is the, I guess, search database, in the form of a retrieval-augmented transformer to implement a general purpose neural circuit for solving many different tasks. You can think of retrieval-augmented transformers as the modern von Neumann architecture of deep learning. But this is not just my analogy. So many prominent works in the literature also explain neural networks and motivate their research with this analogy in mind. But in this talk, I want to take this analogy a step further and see how far we can go by taking it seriously. So the question I'd like to explore in this talk is, what did it take for us to scale electronic circuits into the program software that we have today? And how can we do the same for our neural circuits to create the future of learning software? So to answer this question first requires us to first define what we mean by learning software. And to do that, it's worth reflecting on what it is that program software does that makes it so powerful. So I'm going to argue that the distinctive capability of program software is that it is a tool for manually modeling and manipulating systems. So as an example, biological systems, weather systems, star systems, mechanical systems, traffic systems, economic systems, physical structures, factories, and even sports teams. All of these are systems of variables and relations between the variables that we can model and manipulate with computers. The computer is a universal simulator of any system. So if program software is what enables us to manually model and manipulate system, then what I mean by learning software is software that automatically models and manipulates systems. And that is the goal that I've been working towards in my PhD research so far. So concretely, instead of having humans be the ones to abstract the world into variables for the computer and take actions in the world based on the computer's calculations as we currently do, the goal of building learning software is to reverse this picture, to have the computer automatically generate and manipulate its own variables for abstracting the world into systems of components and their relations. So we can program with goals rather than program with procedures. For example, the manual approach to modeling this system of objects is for humans to abstract the scene into variables, in this case as representations of objects, and write code for the domain-specific language and transformations that process these variables. In contrast, automatically modeling systems means that the agent constructs its own variables from perception, learns transformations on these variables, and grounds these variables into observations without supervision. Instead of manually specifying the goal constraints to satisfy, automatically manipulating systems requires the agent to infer these constraints directly from raw observation and translate its internal interventions into external actions in the world. So electronic circuits are to neural circuits as manually manipulating systems are to automatically modeling and manipulating systems. To manually model and manipulate systems, humans invented tools for abstracting the world into entities and relations. But if we want to automatically model and manipulate systems, the two major paradigms in deep learning today are inadequate for giving us answers on how to do so, because they generally either assume that such abstractions are already predefined by the human, or they learn monolithic representations that do not explicitly represent systems. So in the first paradigm, for example, we see this in supervised learning with human-defined inputs and output spaces, which include natural language, in unsupervised learning with human-defined latent spaces, and in reinforcement learning with human-defined state attributes and affordances. And I'm sure everyone has been quite impressed by the recent multimodal models that can converse about what they see, such as Flamingo from DeepMind. A big reason why these models can interpret these images meaningfully is because they're supervised with human language, which is an abstraction that humans developed. But the question I'm interested in this talk is how these abstractions can be discovered without supervision in the first place, how humans did it for ourselves, and when we came up with these basic abstractions like objects, variables, functions, and relations, and how we can build machines that automatically discover their own abstractions as well. So that was the first paradigm. Now, the other paradigm does not assume human-defined abstractions, but do not explicitly represent systems either of entities and relations. So instead, these approaches represent scenes monolithically and primarily excel in tasks that require a single focus of attention, such as a single face, or a single body, a single object to model, a single object to manipulate, or a single object to control. And empirically, the field has observed that monolithic representations tend to generalize poorly when new objects are introduced. So in this example, the A3C agent performs much worse when a wall is added to the breakout game, even though it performs perfectly when the wall was not added. And monolithic representations also generalize poorly when encountering new combinations of objects, such as in this example, where we see a monolithic visual planning architecture called SAVP that you see on the left, generalize poorly to constructing new block towers, as you see on the right. And even when we do provide human abstractions like language to these models, they often do not bind attributes to entities or model the relations between entities. So paradigm 2 fixed paradigm 1's issue of having human-defined abstractions, but methods under paradigm 2 thus far do not represent systems in a way that generalizes. So what we want is a third option, where the agent constructs its own variables and transformations over them, where these abstractions emerge on their own without requiring the human to define them. So I'm going to show an approach towards this third paradigm in this talk that modifies the learning algorithms for traditionally monolithic methods to enable them to represent abstractions of entities and relations. In other words, this talk will propose suggestions on how we might enable symbolic abstractions to emerge from distributed representations. So concretely, I'm going to talk about 4 examples of the abstractions humans have invented for scaling electronic circuits to modern software systems, such as the digital abstraction, data abstraction, function abstraction, and problem abstraction. I'm going to deconstruct the underlying principles that made these abstractions powerful, use these principles to design neural networks that exhibit many of the same properties and benefits that we get from digitization, variables, reusable computation, and hierarchy without explicitly defining these abstractions themselves. So I'm going to call this line of work neural software abstractions. So here's our monolithic agent as a reference point, which represents the sensory motor interface with the monolithic representation. I'm going to first talk about how we can implement the digital abstraction in neural networks for breaking the monolithic representation into a discrete set of representation of entities, persistent entities. Then I'll talk about how we can implement the data abstraction for treating these entities as variables. Then I'll show how we can implement the function abstraction by representing transformations on these learned variables in a way that makes them reusable across contexts. All 3 of these examples will be in the context of learning representations of objects for downstream composition, because objects are one of the most basic abstractions of the sensory motor interface. My last example will be more theoretical, where I show how we can implement the problem abstraction, similarly to how humans develop conventions for hierarchically organizing program software into nested modular programs. I will show how to coordinate many local agents to achieve the same global objective when using only local credit assignment. So together, these four form one of the most basic abstraction stacks we've invented for scaling electronic circuits to software. And now I'll outline how principles that made each abstraction work can be translated into neural circuits. So the first principle is about how we can decompose a monolithic continuous representation into a discrete set of representations by reframing the representation learning problem as one of error correction. So this is the exact same principle that gave us digital circuits from analog circuits.
Let me show you a quick demo. Let me show you a quick demo.
Okay, so in this video, we're seeing a particular signal being corrupted by noise in the chainsaw. So you have a input square wave in yellow. It's being corrupted by noise in the and the output wave is purple. And as you can see, the output wave is uncorrupted. So now let's see.
So if you look at the
Okay.
So notice that as I put in a lot more noise, then the output begins to go berserk. But as long as my input,
this noise correction property only works up to a certain extent, but it does seem to suggest that with at least from going from analog circuits to digital circuits, we've developed algorithms for correcting this noise and being able to correct errors when we propagate signals. So enforcing this property is what people call the static discipline, which remaps corrupted zeros and ones back into signal ranges corresponding to valid zeros and ones. And this is essentially the key idea that allows us to discretize continuous signal in a faithful way. Now, what this means for neural networks is that the way we can also encode discrete information over a continuous substrate is as the fixed points of a dynamical system. If the value gets corrupted by noise, then the system dynamics pulls the value back to the fixed points. So this insight that discreteness is fundamentally a solution to error correction enabled us to improve the optimization of prior slot-based methods that learn to encode visual scenes into a discrete set of representations called slots. So on the left column, you see the ground truth image of some objects. Then you see the reconstruction, and then afterwards, each column shows a decoding of a different slot, and each inferring a representation of a different object without any supervision on what the objects are. So you can see the error correcting properties here when you see that even though all of the rows are initialized differently, they all converge to the same final set of representations up to a permutation. So implicitly, this network that I'm showing you here that generates these representations is computing an error correction algorithm that allows us to converge to the same representations, no matter what the initializations are. So the way slot-based models work, in particular slot attention from Locatello, is that they're all trained to learn an update rule, similar to an expectation maximization update rule, that gets iteratively applied during execution time to update a random initial guess to produce a final representation that gets fed to a downstream task. So in this sense, you can think of slots as parameters of the components of a latent mixture model, or in other words, as fast weights parameterizing the function that describes each latent object. So to train vanilla slot attention, we would usually backpropagate through the entire refinement procedure, but this leads to difficulty in optimization, as we can see in the uncontrolled growth of the Jacobian spectral norm of the slot attention cell of this particular architecture called slate. And that is what you can see in red. But in contrast, our insight that discretization is fundamentally about error correction, or in other words, computing a fixed point, enabled us to develop a novel method for training slot attention using implicit differentiation, which empirically improves optimization performance, which you see in blue. So if we recognize that, yeah, so it is the, let's see. It is, so for each, so this is the input image. This input image is going to get mapped to a set of vectors. Each of these vectors gets decoded into an image that basically corresponds to only one of the objects. So the vectors, the latent vectors that get decoded into these images are the things that converge to it. Yeah. So as you can see, as you do the iteration, initially the representations might contain multiple objects in one, or they might be kind of messy. But as you iterate this further, you see the representation start to stabilize. So yeah. What?
And what about situations where the continuous substrate has many other minima that are not legitimate decoding?
Yeah, that is a valid concern. And so I think this is generally empirically we see that when we train it to predict, when we train it to reconstruct the image, oftentimes if we have enough diversity of the data, then the minima that it usually converges to is the one that ends up separating the different objects into different slots. However, there are also other minima, which might kind of, I guess, put all the objects in one slot and then put the background in another slot, for example. Those minima generally tend to arise when the diversity of the combinations of the objects that you see in the data set is not diverse enough. That is something that I don't yet know how to fix. Basically the general fix I've mostly been employing is to get more diverse data. Yeah, that answers.
So there is also a third kind of minima that happen at inference time, where you initialize with a tiny bit different noise, and you will not localize the representation of any object per se. You might get half a mask on the cube and another half on the circle, or like both of them very diffuse. Do you see that?
So yeah, so I think what we see with these with slot attention is that either it gets to the right minima for all examples, or it doesn't get to the right minima for all examples. And the reason is because so this is a valid concern for like normal vanilla k-means or like expectation maximization. But I guess if we look, so the modification that slot attention adds to k-means is that it replaces the E step and the M step with our neural networks. And what we empirically see is that the network is trained to learn a good update rule that avoids those bad minima. When you iterate the network during inference time more times, you actually observe that it converges to the correct minimum. But this is only if like the network weights end up learning the right update rule. So if you don't train with diverse enough data, the network weights might actually end up not ever producing slots that are at the correct minimum. Yeah, I think one thing to emphasize here is that we're training a network as an update rule. So during inference time, we can actually roll the network out multiple steps. And the more steps we roll out, the sharper I guess like the better the predictions end up being. Yeah, but I think the third minima generally doesn't happen if the network is trained to actually separate out the objects properly. If it turns out that a particular configuration of the hyperparameters or a particular combination of that in the data set cause the network to not do that for the training set, then it also won't work on consistency. Yeah. Okay, cool. So let's see. Where was I? Okay, yeah. So if we recognize that slot attention is performing a form of error correction, then we can recognize that this is actually an instance of a deep equilibrium model, which is a neural network that solves for a fixed point as an intermediate step, Z star, on the computation graph. So one property of these models is that rather than back propagating through the entire fixed points iteration, it is possible to just compute the gradients with the implicit function theorem without needing to backprop through the iteration. So recognizing that slot attention is an instance of a deep equilibrium model expands the design space of training these slot-based models beyond what is currently done. And what is currently done is just you iterate the slot attention during the forward pass and then backprop through the unrolled iteration in the backward pass. But now we can use any root finding solver to find the fixed point for the forward pass and use any method to directly compute the implicit gradient in the backward pass without storing the intermediate activation to the rollout before the fixed point. So the challenges is in computing the inverse Jacobian term here, which is expensive. So prior works either approximated it using a Neumann expansion or used a root finding solver to solve another fixed point system. And the method we found to be best in our context is to keep the forward iteration as before, but use the first order Neumann approximation of the implicit gradient. And this approximation is not only the simplest to implement with one additional line of code, but it also has the lowest time and space complexity of all the methods that we use. And it turns out that if we use this approximation, it ends up just being a truncated backprop that you can just like add that one line of code in the method.
Layers where the star is putting in the same are other integrated well. In addition to the star are other integrated well in the layer where started to be fixed or not.
Yeah, so it's essentially the
You can show the formula again. Okay. The star comma x.
yes, yeah, so yeah, so Z is the slots, the latent state, and then X is the image. So you run this network by basically so this update rule is a function of the previous Z and the current image, and then you produce an updated Z, and then you use that updated Z and you look at the image again and then produce a better Z. Yeah.
And the very first layer, the Z star as a graph.
As a random initialization. Yeah. No. Yeah. So you just randomly initialize. Yeah. So the goal is to train the network as an update rule to take any random initialization and I guess drive it to like a particular fixed point that like models the particular image that's given as input, which is X. Okay, yeah, so concretely we implement this by basically truncating the backprop, as you can see here. So now to evaluate, we're going to use the latest method that builds upon slot attention, which is the Slate architecture. So it uses a discrete VAE to tokenize the image. It then uses slot attention to cluster the tokens and a transformer decoder to reconstruct the image. And so implicit differentiation gives a lot of optimization benefits. It removes the need for gradient clipping, as you can see here. So validation curve for the vanilla version is in red and pink, which eventually overfits, but validation curve for the implicit version learns faster and does not overfit. And in fact, without gradient clipping, the Jacobian norm for the vanilla version begins to explode as training progresses. And this is reflected in the large gradient magnitudes of the vanilla version compared to the implicit version in the layer norm of the slots. And when we look at reconstruction quality, we observe that the vanilla version sometimes misses the objects, changes their size or changes their colors, whereas the implicit version generally matches the ground truth much more closely. So essentially better optimization translates into better results. And we can also see this quantitatively in terms of the mean squared error, which is almost a 7x improvement. And for other tasks such as set property prediction, we also see better optimization, as you can see in the blue curve here. Using the principle of error correction to learn representations shifts our perspective from treating representations as static data attributes to treating them as these dynamic fast weights that you can continuously adjust via learned update rules. So to conclude this section, I showed how you can implement digital abstraction in neural networks by treating representation learning as error correction. Next, I'm going to talk about the data abstraction, which is about constructing variables as placeholders for data. So our second principle is the principle of symmetry for representing variables in neural networks. I want to especially highlight Rishi Virapineni and JD Correas, who are core contributors to this project. Rishi is a PhD at CMU, and JD is a research scientist at Google. Yeah, so for me, I've always just been very interested in this concept of what a variable actually is. In software, we write variables as a given, but I think with learning system, it's not really clear how to basically represent variables that can be, I guess, where you can write functions that operate on one instance of a variable that transfers to other instances of variables. Like I think this concept of a symbolic variable is very not present in connectionist architectures. And I've always been curious how do you actually like integrate the two. So this is an attempt to try to do that. So we can start thinking about what is a variable fundamentally. And a variable is simply the name of a placeholder for a set of data points, right? So this implies a symmetry in the values of the variable's domain. So whatever operation can be performed on one instance can be performed on another instance. So this is the essence of what it means to be a variable. It's a property that's known as universal quantification. So the actionable consequence of this implication is that if you want to represent variables in neural networks, then you should process latent sets with permutation equivariant functions. So my collaborators and I used this idea to build one of the first world models with slot-based representations that exhibited various of the properties that makes variables powerful. So start off as a point of reference, the conventional architecture for world models use monolithic dynamics and observation models to process monolithic representations H. For our method, we use a slot-based method with K latents instead. And the key idea is to treat all these slots as instances of the same generic object variable by processing them symmetrically. So what this means is that we're going to define the dynamics model to be permutation equivariant, that is sharing the weights across all of the slots. So we use a graph neural network in this paper, but you can also use other equivariant functions such as transformers. So we call this world model OP3, and this is how we use it to plan. We're given a goal image, and the agent interacts with the environment to get get an estimate of the entity representations in the scene. And it also infers the latents for the goals, the goal entities. Then it rolls out the dynamics model to predict the latent entities in the future and compares these predicted latents with the goal latents using a pairwise cost function that for each goal latent matches with the closest predicted entity latent. And so the benefit of representing variables in this way is that it gives you the ability to generalize the function that operates on one instance of the variable to other instances. So we tested this kind of generalization with block stacking tasks. In this experiment, the observation space is an image of a block in the air, and OP3 is trained to predict the effects of gravity on randomly falling blocks. So during training, OP3 sees 1 to 5 blocks, and during test time, it sees 5 to 9 blocks. And the action space is a parameterization of the block's color, shape, and location that OP3 chooses to draw. So what's significant here is that OP3 never was trained to build block towers, and it was also never trained on 5 to 9 objects. So we'll see, which makes this a challenging problem, and we'll see whether our architectural choices allow it to generalize it this way. So these are the goal images, and these are the block towers that OP3 built, which matches the goal images really closely. And OP3 gets 3 times the accuracy of the state-of-the-art video prediction model at the time, SAVP, that does not symmetrically model objects and relations.
So the main is the permutation equivariant?
Yes, yeah, across the slots, yeah. And so let's take a walk through how OP3 grounds its representation in a series of interactions. So it's a very much of a interactive inference algorithm. So we're given an observation at time 0. The inference algorithm decomposes the scene into this case 4 latents using a method similar to slot attention, which we render independently here with the observation model. So here you can see the green object and the hard to see, but it's the brown object right here. Green object, brown object. So this showcases that these latents exhibit many of the same properties that we expect from instances of variables. In particular, for example, like you can see that each latent has its own memory register, right? It's just the slot ID. And what this allows it to do is it allows it to be independently rendered and evolve through time. So you can ask, what is variable binding in this context? Well, variable binding is exactly just inference on what the representation of each lane should be given the image. So given the pick and place action, OP3 then predicts how the objects would evolve and updates this prediction using the observation after taking that action. And notice that these that OP3 translate these actions into modifications of the latent variables across time. So here looks like it's moving the brown, it's moving the brown object here, and it just and keeps the green object the same. So the representations are disentangled in this sense. And another nice property of variables that we get with these lanes is spatial temporal consistency. So the green object is always in the first slot. The brown object is always in the last slot. We don't have any mixing through time. And this also enables OP3 to handle occlusion, because even if objects are occluded in the observation, the latent representation of that object persists in their own memory register. So OP3 is thus a world model that discovers and binds its own variables for describing its observations without any human specification on what the variables mean and what they correspond to. So here we don't tell it which objects to model. It's just uses a slot-based approach and ends up putting the information to different objects into different slots. And so this is a brief visualization of how planning works. We're given initial observation and a go image. OP3 interacts with the environment to refine its estimate of the entities in the scene. Then given that representation, it rolls out the dynamics model multiple times in the future and uses model predictive control to select the best sequence of actions to execute. We also applied the OP3 world model to real world videos from the Berkeley robotic cloth dataset. And as you can see, there's much variation in the lighting and geometry of the objects that make it much more challenging than the synthetic domains. One very interesting phenomenon we observe here is that the OP3 inference algorithm takes both time and actions into account, so it can use this information to go beyond simple color segmentation. So as you can see at time step 0, it actually groups, at time step 0, it actually groups the red towel and the red robot arm in the same slot here. But over time, it realizes that they should be in different slots and learns to separate the robot arm into the first slot here and the red towel in the last slot here. So in the first time step, there is no signal for it to know that these are separate objects, but from interaction, it realizes that they should be separate. So this was a very interesting emergent property that came out of simply just having this slot-based architecture in modeling videos. And so I think that the lesson to be learned here is that it's generally insufficient to learn representations of objects from only static images. We need information from for how objects change over time in addition. So in this way, this is an example of acting as a form of learning. The feedback from the environment over time enables OP3 to dynamically adapt the estimate of what it thinks the objects in the scene are.
Can I ask a question?
Yeah, go.
So what forces the different slots to gravitate to different objects in this case?
Yeah, I think it is simultaneously so the architecture fundamentally is something like a latent mixture model. We're basically doing, we're doing filtering with a latent mixture model. And so the latent mixture model has a particular inductive bias, which is the bias that the centroids of the mixture model are a priori independent. And so the update rules for a mixture model kind of are consistent with that particular prior. And what we do here with these slot-based models is that we basically keep the same structure of the filtering with the latent mixture model, but just replace the sort of update rules with neural network mappings. And what seems to be the case is that the reason why these objects end up, being put in different centroids is a combination of that particular inductive bias and the data that we give, I guess. And it could be the case that it decides to learn to not do that, but empirically that seems to be what happens, I guess, when we impose that particular inductive bias.
We can check this, right? We can initialize it to be the t=0 state, the slots, and
Mhm.
then see if it disentangles.
Yeah.
Instead
So
of initializing the slots, the identities of the slots random.
yes. So we do that. So initializations of the slots are random.
Or you can choose to not have them be random, and then see here and still be consistent with the dynamics of the scene. And if the model does not now make them separate, then you know that it could have learned the other one also.
Yes, so that certainly seems to be a very real possibility. I think that like there are certain, I guess there are some engineering things that we need to do in order to like certain hyperparameters that we need to choose properly in order to make it such that it does have this property for different scenes. Once we do choose those hyperparameters properly, then for other scenes in the same distribution, it ends up producing slots properly as we expect. However, there are some cases where if we choose the hyperparameters improperly or change the architecture in different ways, then it could also learn to produce different. So that is certainly a real possibility. And I think that is one of the open questions on how to like properly control this. I think that is the part that, yes, I think is still, it's like, yeah, so far it's, I think the status of the knowledge on how to do this is something like this kind of inductive bias and the type of diversity of data is sufficient to be able to give us these properties. But it's not yet fully understood how to get this reliably in cases. Yeah.
When you're planning, when you're comparing your people, like you're doing this on the like full image analysis, because the spatial and temporal, like if you like guarantee between like the goal image as well, or it's just
yeah. Oh yeah. That's a good point. So during so I guess you're raising the question of the indices of the goal latents might not match the indices of the predicted latents. Yeah, so we first perform a matching algorithm to find the minimum cost match, and then use that as the way to as the indices for the goal for us to compute the cost.
why not do it? Well, I'm not super but could you not do the image itself from this line? This compare images instead of comparing slot.
Yeah, we could do that. I guess it's more expensive. Yeah, because I guess the main reason why we would want to represent the scene in terms of slots is because we're basically comparing like five lower dimensional vector from with like a big image, which is less semantically, I guess, like each pixel value might be less semantically meaningful than like comparing the vectors corresponding to the objects themselves. Yeah.
So is this particular representation trained with exactly like what was the domain of this?
It was trained to model the Berkeley clock data set. Yeah. It was not trained on a different way. So like for different
data set is with X robot playing around with
yes, this exactly. Yeah.
with this particular clock.
There were other clots. So like, yeah, there were other clots. Yeah. Okay, so concluding this section, permutation world models are useful for modeling these slots symmetrically. And it gives us many of the properties that makes variables powerful in traditional software, such as consistency and permanence. But it also gives us new capabilities from neural networks, such as adaptation to new information, which manually define variables. All right, so next I'm going to talk about function abstraction, which is about collapsing the combinatorial space of variable transformations into a set of functions that can be reused in different contexts. So in the, let me highlight Lee Diane, who is Lee Diane and Amy Zhang, who were also core contributors to this project. So Lee is a PhD at Berkeley, Amy is a professor at UT Austin. In the previous two sections, I described how you can use slot-based methods and equivariant dynamics models to automatically model systems. This addresses what I call the correspondence problem of inferring entity representations of entities in such a way that there's a correspondence between transforming the agent's internal representations and taking an action to affect the object in the real world. So now I'm going to transition to talk about the control and planning problem of manipulating systems. So at the highest level, any kind of manipulation can be reduced to reconfiguring the components. So we can study this concretely as an object rearrangement problem. The challenge to solving this kind of task is that the space of possible system configurations is combinatorially large. So here you see the same state transition for a single object, but shown in different contexts, whether the background objects are in different configurations or the target object itself is different. So if we want to monolithically represent the scene, we would not express the appropriate problem structure that enables us to design algorithms that represent transformations in a way that can be reused in different contexts. So our goal now is to represent reusable functions. And the third principle I'm going to discuss is that the functions that are independent can be reused. And how we're going to implement this independence is we're going to abstract the visual transition into a state transition that throws away information about the specific entity and the context. So if we can do that, then we'll be able to reuse our representation of the state transition on different entities in different contexts. So to do so, we're going to construct a two-level hierarchy. First level maps each image into a visual transition into a set of slots. And we're going to enforce that each slot is split into two parts, an action-dependent part, which we're going to call the state, and an action-invariant part, which we're going to call the type. And then for the second level, for any inferred entity transition, we can extract the transition between the state, between its states, and cache this state transition in a separate external memory that we can query and reuse for later problems. So the way we're going to do this is the following. So in the first level, we're going to do something similar to OP3, which is to train a world model and apply the dynamics model only for the state part and just directly copy the type into the next time step. And the second level of the hierarchy, we're going to cluster over entities that share the same state to construct an abstract transition graph where nodes correspond to states and edges corresponds to transitions between states. So these edges are thus our independent representations of the transformations, entity transformations that are agnostic to the type and context. So I'm going to talk about how we can use this for planning and control. So we first are given an initial observation and a goal. We use the world model to infer entity representations as goal constraints from the goal observation and the current entities from the current observation. So as you can see, the indices are actually unaligned. So we're going to use a Hungarian algorithm to align those indices. And we're going to select an entity to affect, bind the entity at this index to a node in the graph. This is the attention mask for the abstract node in the graph, for the selected entity. This is the attention mask for the abstract node in the graph. And we do the same thing for the goal constraints. And in that abstract graph, the edge between those two nodes is tagged with the action that caused the transition between one node and another that we had collected from the training set. Take that action in the environment, observe the resulting observation, and now we see a new observation and repeat the process. So notice that these edges, whose nodes we bind to, are agnostic to the type and context of the objects. And we just keep on doing this until we finish solving the task. And because the state transformations are agnostic to the entity type and the context, we can train on only 4 objects and generalize to 5 objects, generalize to 6 objects, generalize to 7 objects, and generalize to 8 objects. But it also makes mistakes. So here are some mistakes. It fails to move the yellow ball here, fails to move the green hammer. Here it makes multiple mistakes. And here it swapped the position between the red and purple cubes. But despite these mistakes, overall, the method outperforms various different offline RL and model-based algorithms, including MPC, with the slot-based dynamics model. Because this is solving this is a particular longer horizon task that requires the rollout, that causes rollouts to actually lose fidelity really quickly. So result is consistent with a bunch of couple of other environments, including block rearrangement, block stacking. And just moving slightly faster just because just wanted to be cognizant of time. Yeah, do you have a question about that?
Does the consequence that blocks that one of the blocks that are above it all over?
No, that is not taking this into consideration. Yeah, so very good point. So currently the method is limited in the sense that it does not model the dependence across objects. But I think that one thing, so it does not do that. I think that will be interesting directions for future work. But I do think that this particular scheme makes it this scheme of mapping objects to these variables that satisfy these constraints and doing a graph search to be able to satisfy these constraints is a nice representation such that we can leverage the symbolic constraint satisfaction algorithms to be able to handle those dependencies. So it will be an addition of that flavor to the current method to be able to do that. Yeah, so concluding this section, I show you how you can implement function abstraction by enforcing representations of transformations to be independent by factorizing out common information. And so with these examples in mind, I want to step back and highlight a running theme underlying all these methods of abstraction, which is this idea of finding equilibria through iterated computation. So instead of learning representations via traditional mappings like Z equals f of x, all these approaches instead start with a random guess and learn update rules to refine that guess until we reach an equilibrium. So this was the case for breaking monolithic representations into discrete set of entities. This was the case for adapting these representations based on temporal feedback, and also using k-means to generate these clusters for grouping the state transformations together. And you can also see this in broader trends in the community where behind large generative models and large language models, such as diffusion models, or predicting updates to reasoning states with scratchpad training. So in my last example, I'm going to talk about a different type of equilibrium that could help us coordinate behavior at different levels of hierarchy. So this is what I call the problem abstraction. And I'm going to show how to design an incentive mechanism such that the Nash equilibrium of a set of local agents solving local problems coincides with the optimal solution to a global problem. So I want to highlight Sid Kaushik, who is a core contributor to this project. He's now working at Samsung. What I mean by abstracting problems is represent problems of different scopes. In traditional software, we invented methods for organizing computation into different scopes such that the modules can be modified without knowing about the global context in which they're used. But in machine learning, everything is in the global scope because the same error signal is back propagated to every parameter. So if we want to be able to abstract problems hierarchically, then we need ways to coordinate agents that solve local problems in a way that solves the global problem. And many large-scale systems follow this structure, where the global optimization emerges as a consequence of solving many local problems. So concretely, our goal is to construct an incentive mechanism in a way that the Nash equilibrium of the local agents coincides with the optimal solution of the global agent, such as the society of local agents can be faithfully abstracted to solving the problem of the global agent. So this can be, this can keep going for more levels in principle, where we build higher level societies corresponding to different levels of scoping. So we're going to consider the sequential decision-making setting, where instead of the usual setup where a global agent chooses actions to take in the environment, we're going to set this problem up as a series of options such that the actions compete to be chosen. And then we're going to try to design an incentive mechanism for the entire society to still be optimal. So the first step to setting this problem is to frame the MDP as a market, where we define the valuations in terms of other agents' bids by coupling the agents at consecutive time steps in the same game via a series of economic transactions. So in fact, this idea was actually discussed 20 years ago in a paper that introduced the Hayek machine, which observed that the optimal choice of the agent's auction bids should be their optimal Q values. But the problems that they left open, which we addressed in this paper, is what is which auction mechanism to use that guarantees this kind of optimality. So our contribution is this insight that we can force the agent to learn to bid the optimal Q value for their action by leveraging the truthfulness property of the second price auction mechanism, which incentivizes each agent to neither bid higher nor lower than the true optimal Q value. In this way, the auction bids of these local agents end up computing the Bellman update. So this ensures that the Nash equilibrium in the local auctions coincides with the optimal policy for the global. So each agent only solves a bandit problem of what to bid, but the transactions across the entire society collectively compute the Bellman update. And so what's significant about this is that each local agent is trained only with local credit assignment without knowledge of the global problem the society is solving, which thereby implements this local scoping that we saw in the beginning. So to conclude, I showed how you can implement problem abstraction by designing incentive mechanisms for aligning the Nash equilibrium of competing local agents with the global optimization problem of the society, thereby creating an abstraction barrier between global and local problems. So to sum up, I showed 4 examples of how we can take the principles behind abstractions that enabled us to scale from circuits to software and apply them to neural networks. I showed how to implement the digital abstraction via the principle of error correction. I showed how to implement the data abstraction via the principle of symmetry. I showed how to implement the function abstraction via the principle of independence. And I showed how to implement the problem abstraction via the principle of competition. So once we see that it's possible to transfer these abstractions over, we see that this analogy between electronic circuits and neural circuits reveals so many new areas of research to bring the principles of software engineering to neural models. So some of these areas people have already been working on, such as understanding how to implement and verify input-output specifications for neural modules. Some other areas like version control or polymorphism or universal communication protocols between models are still open problems. I think if you guys are able, so I could stop here, go for questions, or I could talk for another 3 minutes on about like, I guess, future work, I suppose. Happy to do whatever you guys would like to do. Yeah, okay, cool, sounds good. Okay, so now I want to take a step back and think about how this research fits into the big picture. So if we think about how AI relates to society, we generally think about AI as a tool for enhancing how humans interface with the world. So this is an essay from Brett Victor that I really like, which states that a tool is something that converts what humans can do into what we want to do, addressing human needs by amplifying human capabilities. So from this perspective, we can think of technology as a lever that enables humans to maximize the impacts of their ideas while minimizing the effort it takes to expend to realize those ideas. So we can think of technology as this communication channel, and the higher the bandwidth, the more leverage we gain. But if we look at this perspective as applied to computers, in many ways, this is not the situation we're in at all. So as I mentioned earlier, often it is the humans that are trapped as the bottleneck between an increasingly powerful computer on one side and a very complex world on the other side. So instead of humans telling computers what to do, right now what's happening is the computers are the ones telling us what to do. You can think of the Uber driver following Google Maps, or I guess humans as physical liaisons to ChatGPT. But if we want to make progress, we need to free humans from being the bottleneck between computers and the world, and so that we can use computers as the technology that they are. So this boils down to working on 2 interfaces. The first interface is between the computers and the world, and thus far my research has been on developing this interface to enable machines to discover their own abstractions for automatically modeling and manipulating systems. But I also think that right now is a very opportune time to work on the other interface, which is between the human and the computer. So there's always been a gap between modalities that are intuitive to humans, like speech, language, drawings, gestures, and what can be understood by machines, which is code. And historically, humans are the ones to bridge this gap. But this is far from ideal because shoehorning our thoughts into code requires overcoming a huge barrier to entry. Even people who do not know how to code must learn new languages or frameworks before they can even people who do know how to code must learn new languages or frameworks before they can even do anything. But as you can see, with recent advances in big models, we finally have the opportunity for the computer to bridge this gap instead. So as we've seen with GitHub Copilot, which translates natural language into code, as well as ChatGPT, which explains code to humans. But going forward, I think that language alone is a poor medium of communication if you want to understand systems. So if humans want to understand systems, then we draw diagrams or we gesture. We have so many more modes of communication other than language, and I believe it is crucial for us to leverage these additional modes of communication to communicate more effectively with machines. So this is an example that I really like, which is, so some early work from GPT-4 shows that it's possible to translate hand-drawn diagrams into HTML code. And I think now is the time where we can start actually scaling these kinds of ideas up. And the long-term, I hope for this direction is for humans to communicate with machines as easily as we do with colleagues at a whiteboard. So this is where I'm going to be taking my work next as a research scientist at DeepMind. So anytime there's friction with communicating with machine, that is a problem to be solved. If we want to build assistive agents for augmenting the human creative capacity, which I want to do, then I believe it is crucial to understand the human side of the AI problem and develop human-computer interfaces that support the human. So I presented in this talk a vision for the role of AIs in society, first presenting my PhD work on interfacing the computer and the world, where I describe neural software abstractions for automatically modeling and manipulating systems, and then presenting my future goals for building the next generation of human-computer interfaces, with the ultimate goal of integrating both to building assistive agents for augmenting the human creative process. So with that, I'll conclude my talk and am happy to take any questions.
Great, thank you. Any questions?
Yeah, I think I was just going with competition. So you have different local agents. How does that work?
Oh, sorry. Each agent is a different action.
Oh, okay.
Yeah. So the option is at this particular state, which agent is for this given which agent is this state most valuable to?
So like, if you essentially if you're driving along, it's like, all right, right, left, or straight.
Yeah.
The three agents are right, left, or straight. Yeah.
That's right. Yeah.
So you build high level abstraction for when level of variables. Is it possible to go backward? I'm observing this, and I can go one step backwards and build some kind of abstraction that's lower level, and it kind of works like say optical flow, but not exactly optical flow, kind of like external representation for a low level but high dimensional object. Do you think that's a possibility? Does it happen in SFI?
Let me just make sure I understand what you're saying. So when you say building a representation of optical flow, how does that relate to going backwards?
In terms of the hierarchy of abstraction. So you're not yet at the level where you separate out data or say separate out objects. But you have to do one step more than it doesn't necessarily have to be optical flow. It's level data.
Yeah, I see. And the goal is sorry, can you remind me?
Yeah, so do you think that this is like this is built this big system where it kind of it has some kind of internal knowledge of how the dynamics of walls are defined, separate out the object.
Oh, I see. Yeah, I see. Yeah. Yeah, so that could be, let me see if I can have a diagram to help with this. Okay. Yeah, I guess like the modeling choice that we're making when we construct an architecture like this is that we want to map pixel observations into a discrete set. And this discrete set evolves over time with a particular kind of with a particular type of interaction, namely like these pairwise interactions. And so we're kind of like, so that is the bottleneck that we're like pushing information through between time steps. So I suppose that with respect to optical flow, I guess whether or not, I think that's fundamentally like an interpretability question, I suppose, like just testing whether it's actually doing this. I haven't tested it myself, so I'm not sure. But I guess the answer would look something like for these two endpoints, which is discrete sets and like video frames, what is the information necessary to like put through this slot bottleneck in order to model the future frames properly? So whatever abstractions are useful for doing that, that is what I would expect the model would learn. Yeah, I suppose. So I guess that would be the starting expectation, and then we can like, I guess, probe the CNN representations to see if it's like actually like learning something like that.
Okay, I think we'll conclude, but let's thank Michael again